Alrighty, 7-4, properties of cardiac muscles. Just what you wanted to know. Exciting. Alright, cardiac muscles. Remember, there's 3 different types of muscles in the body. Striated or skeletal, involuntary or smooth, and cardiac. So, what are some properties of cardiac muscle? First of all, they are also striated, like your skeletal muscles, and they constrict by using the sliding filament model of skeletal muscles. So they kind of do the same thing. Remember, that thing? Yeah, they do that. The cells are much shorter, though, because if you remember, skeletal muscles were very long and skinny. These cells are much shorter. They're kind of on the fat side. They're branched. Instead of having just like one blunt end, they can branch a whole bunch of times. And they are interconnected, so they're all linked together. They have usually 1 or 2 very large, centrally located nuclei. Their intercellular spaces, that would be the spaces between the cells, are filled with connective tissue, which is called endomysium. If you remember, endomysium is kind of like the endo inside. Mys means muscle. So endomysium was like the, almost like, well, I was going to say like the sarcolemma, but not really. Alright, they also have something very special and unique called intercalated discs. They're wavy junctions between 2 adjacent cells. Because the edges of their cells are wavy, when 2 of them fit together, they make a very strong, tight bond. And so that waviness that is created is called an intercalated disc. They also have these special things called desmosomes, which are kind of like a superglue. Superglues the cells together. And then we have gap junctions, which are little holes that, like that, they line up perfectly, and that allows ions to pass from cell to cell so they can talk to each other. So even though the heart is made up of a whole bunch of several cells that can work independently of each other, they all work together as one unit. So this is called functional syncytium. Now if you remember, that word syncytium means to work together. And so functional syncytium is just the word used to describe the fact that the heart, all the muscles work as one muscle as opposed to several teeny tiny individual ones. Alright, so let's take a look at a picture. So here's some of the main features that we said about cardiac cells. So here's some big old fat nuclei. You can see these in here. You can see the little wavy intercalated discs. We can see that the muscles themselves are kind of striated, not as much as skeletal muscle. We have gap junctions, which are these cute little flower looking thingies. We have the I forgot the word. Oh my god. Desmosomes. Oh my god, I could not remember the word. Sorry. Or fasciae adherens. That's a fancy word. We'll just go with desmosomes. And so that's the super glue right there. Looks like hot dogs. Hot dogs. And then we can see that the cardiac cell itself branches off and kind of becomes one with another cell. So they're all kind of bundled together. And their mitochondria, there's actually room in there. Remember, in skeletal muscles, there were too many of the myofibrils for the mitochondria to fit on the inside. So they were shoved to the outside. So here they're actually shoved on the inside. And there's a ton of them because the fact that that the muscle needs a constant supply of ATP and energy, you have to have lots and lots of mitochondria. Alright, so the large mitochondria and the large number of them provides enough energy so the heart doesn't get tired, because that would be bad. They contain A, I, and Z discs, just like a skeletal muscle does. And they have smaller sarcoplasmic reticulum than skeletal muscle cells. Alright, so what are some differences between cardiac and skeletal muscles? First of all, how they get stimulated. Usually for skeletal muscles, every single cell needs a neuron, a motor unit attached to it. But on this one, some of the cells, they can just go, and jerk on their own. They don't need any outside stimulation. So some of the cells in the body, or in the heart, are self-excitable, and they can initiate their own depolarization, which can then pass it on to the next one, and so on and so on. We call that automaticity or autorhythmicity. And so what happens is it's kind of like dominoes. Once one cell jiggles, then all the rest of them decide to go. There's this cool experiment. You take a petri dish, you take a heart cell, you put it in there, and he just kind of, does his thing and twitches. You take 2 cells, and they each kind of do their own thing. But when they touch each other, hey look, they go together. And so that's kind of what's neat about them, is that they can communicate with each other. Whereas a skeletal muscle, they need a neuron to stimulate it. Now, don't get me wrong, there are neurons that stimulate the heart, but there are some that are able to do it all by themselves. Dang it, my cat is eating grass For those of you who have cats, you know what that means. I'm going to have a hairball in my house soon. All right, second thing that makes them different. Organ versus motor unit contraction. The whole heart either contracts or doesn't contract at all. There's not like, remember your thigh muscle, depending on how much you want to use, you can do one motor unit, all the motor units, some of them. So your heart isn't like that. It's not like, well, I'll contract here and here, but not there. It's either it all contracts or nothing at all. Due to the fact that we have depolarization passing from one cell to another through the gap junctions, that allows the heart to continue to work all at once. Thank you for bringing me a snail.
You're welcome.
Why did you bring me a snail?
Because I thought it would be cool for you. Because the shell was getting too big and it was getting dried out. So I picked that off and see, look, now
Cool.
he's coming out.
Now go find him a house because this is really hot metal and it's going to burn his little legs. Or foot.
There.
Whatever. Go put him in the grass. Okay.
Yeah.
Anyway. Oh, now we got snail goo on our brand new table. Ugh. So the skeletal muscle, it has to contract as motor units, which means all, some, parts, we're heart, all or none. Okay, third thing, the length of the absolute refractory period. If you remember, after a muscle contracts, there's an amount of time where we have to wait for everything to go back to normal. Calcium has to go back in, sodium levels have to go back to normal. And so for heart, it's a little bit different. The heart contracts for about 250 milliseconds, which for skeletal muscle is anywhere between 20 to 100 milliseconds. So the heart contracts much, much longer than skeletal. But the refractory period is just about as long. You cannot go beep, beep. It has, well, you can because I'm not that fast, but it has to wait at least another 250 milliseconds before it can beat again. Whereas a muscle, only 1 to 2 milliseconds before you can recontract your muscle again. This prevents tetanus. Remember tetanus? The quivering of the muscle. Remember what we did with your putting the things on there? And so this prevents that because that is called, dang it. Sure. Oh, I can't remember the name, but it's a quivering of the heart when all the muscle cells are contracting independently of each other, and so all your heart does is quiver, which means it doesn't pump blood. And that's usually when you can re-shock it and kind of slap them all upside the head and go, hey, beat together. Okay, some similarities between heart contractions and I think I meant to say heart muscle. Yes, you can have one too. So about 1% of the cardiac muscles are autorhythmic and help to pace the heart. What?
Can I go to the place this one?
Not by yourself?
I know, Kira's coming.
Yes. So 1% of the heart muscles are autorhythmic, and none of your skeletal muscles are, and they help to pace the heart. They make sure that your heart's going at a good rhythm, not too fast, not too slow. You can have higher and lower heartbeats. It's called tachycardia and bradycardia. Usually that's a condition of something else, but some people just have naturally higher heartbeats. For an average adult, here comes the cat, with claws. The average adult heartbeat is 72 beats per minute. Athletes tend to have much lower, and then you can have higher for various other reasons. The rest of the heart muscles are contractile, and so the 99%, they're the ones that respond to the autorhythmic ones. And we'll talk more about that part later. Okay, sequence of events, what goes on in a heartbeat in terms of the contraction part. And so I have these things right here, and you're going to notice that these go with the numbers on the next picture. So I'm going to go back and forth, back and forth. Okay, 0. During the 0 phase, there's an influx of sodium ions into the cells, and that causes a spike in sodium levels. Okay, ready? So now I'm going to show you the picture. There we go. So during right here. So here's the spike of sodium. You can see it right here. Influx of sodium is very rapid as sodium is coming in. Okay, now we go back. 1, the sodium gates close. So once all the sodium gets in, it slams shut, so no more is allowed to come in. So we go back over here. 1, sodium gates close, so there's a quick little drop right there. Okay, next. 2, the depolarization wave moves down the T tubules, causing the release of calcium ions into the sarcoplasm. Basically, calcium levels increase. So, 2, calcium levels increase. But we call this stage the plateau because nothing really is going on in terms of change of voltage. Okay, and then 3, excitation and contraction coupling. So that's the actual, this thing. As cross bridges are formed, calcium gates are closed and is pumped out, so it can do it again. And now the potassium gates open. Okay, so 3 right here. Potassium gates open, which let them out. and then everything's starting to restabilize. And then we get to 4, which is refractory period, which is no more contraction. And so if we go back, so we can see 4, and then it kind of picks up over here, 4, and then all of a sudden sodium levels shoot up again, and it starts all over again. All right, and the last couple of things, energy requirements. Because the heart, because the heart is pumping over and over and over all the time for your whole entire life, it needs a constant supply of ATP. So it relies on aerobic respiration because of the high ATP yield as opposed to anaerobic respiration. It usually uses glucose and fatty acids as their fuels to break down to do aerobic respiration. And so there's lots and lots of mitochondria inside of your heart muscles to show the fact that your heart is so dependent on that ATP. So what happens if you can't get enough oxygen to the heart in order to do aerobic respiration? You get something called ischemia. And ischemia is the condition of having a lack of oxygen to the heart. Or you have an ischemic attack, which is basically saying a little part of your heart muscle is not getting enough oxygen. So what happens is that your heart starts to switch over to anaerobic respiration, which is bad, specifically lactic acid fermentation. All this lactic acid buildup in your heart prevents the heart from making ATP working properly. And then when that ATP is not working properly, the gap junctions close. And when they get closed, they don't pick up signals from the other cells around them, and so they just stop working. I'm done, no more. And then that leads to usually a heart attack. So you can see right here, here's the area of ischemia, so no oxygen. Here's injury, so this part is actually starting to get damaged by the lack of oxygen. Here's the infarct, which is the actual heart attack, and then electric force due to it. So it actually changes the polarity of the cells outwards from there. All right, so many causes for heart attacks. Ischemia just happens to be one of them. All right, say goodbye. Bye-bye, cat. Wait, how's that go? The cat beard thing? Okay. I'll see you guys tomorrow. Bye.